All right, let's just jump right in. I want you to picture something for me. 150 gallons of oil. That's a lot of fuel, right? We're talking enough to drive a car for thousands and thousands of miles. Just keep that image in your head for a second.
Because, believe it or not, all of that energy, every single drop, is packed into this right here. A tiny, single ceramic uranium fuel pellet. It's smaller than the tip of your finger. And that incredible energy density is the secret we're going to unpack in this explainer.
So, today we're figuring out how a nuclear power plant really works. Yeah, we're going to go way beyond just looking at those giant cooling towers. We're diving right down to the heart of the atom to see how this incredible technology actually makes electricity. Okay, so first things first, the big fundamental challenge. We all know there's a ton of energy locked up inside an atom. The real question is, how in the world do you get it out? And not just get it out, but get it out in a way that's controlled and, actually useful. Well, the answer is a process called fission. The basic idea is actually pretty simple. You take a neutron and you fire it at a heavy nucleus, something like uranium-235. When it hits, bam, it splits the atom apart. And that split releases a huge amount of energy. And this is the important part. It also releases more neutrons.
Let's break that down, step by step. First, you've got a neutron, moving at just the right speed that slams into a uranium-235 nucleus. Second, that impact makes the nucleus super unstable, and it just tears itself apart, splits violently. And third, what comes out? You get two smaller atoms, a massive burst of energy as heat, and here's the key to the whole thing, 2 or 3 new neutrons.
Right, so those new neutrons we just talked about, they're the real game changer. Why? Because each one of them can go on to split another atom, which releases more neutrons, which split more atoms. You get the picture. It's a chain reaction. And that brings us to the next big challenge. How do you tame that? How do you keep it from running away and instead turn it into a source of steady, reliable power?
The magic word here is criticality. And I know it sounds kind of intense, but it's not a scary thing. It just means perfect balance. All it means is that for every atom that splits, exactly one of the neutrons it releases goes on to split another atom. Just one. That keeps the reaction going at a perfectly steady, constant rate, just humming along producing heat. If it's more than one, power goes up. Less than one, the reaction fizzles out. So K equals 1, that is the sweet spot.
So how on earth do you maintain that perfect balance? I mean, we're talking about subatomic particles here. Well, the answer is, it's one of the coolest and most surprising little quirks in all of physics. It's a tiny detail that makes the whole thing possible. And it's all thanks to something called delayed neutrons.
Okay, so get this. This is why they're the secret ingredient. When an atom splits, over 99% of the neutrons fly out instantly. They're called prompt neutrons. But a tiny, tiny fraction, less than 1%, are delayed. They kind of lag behind, popping out a few seconds later. And that little delay, that's everything. It acts like hitting the brakes on the whole reaction, slowing the response time down from millionths of a second to whole seconds. And that gives our clunky mechanical systems, the control rods, plenty of time to actually move and keep things in check. Seriously, without this tiny group of slowpoke neutrons, controlling a reactor would be basically impossible.
All right, so we've got a perfectly controlled chain reaction making a ton of heat. Awesome. What's the next challenge? Well, now we have to turn all that atomic heat into the electricity that actually powers our stuff. And you know what? This part is probably a lot more familiar than you think.
It all starts with making steam, and there are basically two main ways plants do this. On one hand, you have the pressurized water reactor, the PWR. In this design, you've got super hot, radioactive water in one loop that never leaves the containment building. It just heats up a second, completely separate loop of clean water, and that's what boils into steam. Then you've got the boiling water reactor, or BWR. It's way more direct. It just boils the water right there inside the reactor to make steam.
So let's look at a quick comparison of the trade-offs. The PWR, on one hand, runs at an incredibly high pressure to keep that first loop of water from boiling. It's more complex with 2 circuits, but the big upside is the turbine never gets touched by anything radioactive. The BWR is simpler, right? Just one circuit. But the downside is that the steam spinning the turbine is slightly radioactive while the plant is running. So it's this fundamental design choice. Do you want more complexity to keep things separate, or do you want simplicity and efficiency?
But honestly, once you have the steam, it doesn't matter how you made it. From this point on, it's pretty much just a classic power plant. The steam spins a giant turbine. That turbine spins a generator, which makes the electricity.
Then, the leftover steam gets cooled back down into water, and that water gets pumped right back to the beginning to get heated up all over again. You've heard people say it, but it's true. The nuclear part is just a really, really fancy way to boil water.
Okay, let's talk about the big one. Safety. When you're dealing with this kind of power, and with radioactive materials, you have to ask the most important question. How do you design a system that can contain it all, absolutely no matter what happens?
The whole philosophy behind nuclear safety comes down to one core concept: defense in depth. The idea is actually really simple, but it's incredibly powerful. You never ever rely on a single thing to work perfectly. Instead, you build multiple, totally independent layers of safety. That way, if one layer somehow fails, there's always another one right behind it, ready to do the job.
And a great way to think about this is like one of those Russian nesting dolls. You've got barriers inside of barriers. The very first barrier is the ceramic fuel pellet itself and the metal tube it's in, the cladding. That traps most of the nasty stuff right where it's made. That's inside barrier number 2, the reactor pressure vessel, which is this massive container made of super thick steel. And then, enclosing all of that, is the final barrier, the huge, iconic containment building. We're talking a fortress of steel-lined, reinforced concrete that's built to withstand almost anything.
Now, here's something really important about safety that might surprise you. Even after you shut down a reactor, meaning you stop the chain reaction, the fuel doesn't just go cold. It keeps generating a ton of heat from the simple radioactive decay of all those split atoms. It's called decay heat, and you absolutely have to get rid of it. And that's exactly why these plants have multiple, redundant, fail-safe emergency core cooling systems whose only job is to be ready at a moment's notice to pump water into that core and keep it cool.
So, we've seen how the plant works, and we've seen how it's kept safe during operation. But that leaves a pretty big question, doesn't it? What happens to the fuel after you're done with it?
And that question brings us to our final piece of the puzzle, the whole life cycle of nuclear fuel. We're talking about the long-term challenge of managing this stuff from the very beginning to the very, very end.
You know, the fuel's journey starts way before it ever gets to the power plant, and it continues long, long after it leaves. It all starts with mining and enriching uranium, which is then made into fuel rods. It spends, maybe 3 to 6 years inside the reactor generating power. Then it's considered spent, and it goes into a big cooling pool on site for several years. After that, it's often moved into these massive concrete and steel containers called dry casks, still on site. But that final step, permanent disposal, that's the real challenge.
And this really is the ultimate challenge. The long-term plan for this spent fuel is to seal it up in super durable containers and then bury it deep, deep underground in a place with really stable geology. The whole idea is to isolate it from the environment for the hundreds of thousands of years it's going to take for it to become harmless. The thing is, we have the technology to do this. The hard part has been finding a location that everyone, scientists, politicians, and the public can agree on.
And that really brings us full circle to the fundamental trade-off. On the one hand, nuclear power gives us a massive amount of carbon-free energy from a ridiculously small amount of fuel. It's incredible. But on the other hand, it leaves us with this waste problem that we have to manage for literally hundreds of thousands of years. So the question is that trade-off worth it? That's the question right at the heart of the entire conversation about nuclear energy.